Hello. All right. Thank you for that, Kishel, by the way. I'm going to present an introduction to classification of handwritten digits or digit recognition. I think a lot of you know the machine learning preamble, so I will just say that this is a classification technique. I want the machine to say, that's a 0, and you go, good job. We're given X train, Y train, X test, Y test. We're not always given Y train, but this case I am. And they're split for me already. So you don't really choose your own split. And it's supervised if I choose to use Y train, unsupervised otherwise. And I use a supervised algorithm in all the cases with the exception of k-means. Yeah, so I use two data sets for performance evaluation. I use the US Post Office of Handwritten Digits, which is much smaller, but it's more tricky. By more tricky, I mean you can sort of perform transformations on it. And I use the modified NIST or MNIST database, which is much larger and a industry standard, really. And this is what a digit looks like. And I know you know what a digit looks like, but this is what it looks like as a representation of a matrix. And we're not going to be feeding in PNG files. We'll be feeding in matrices that have pixel values that represent it. You can see the pixels. Yeah, so let's get into the algorithms. I start with 4 distance-ish algorithms. The first one is k-means. The essential idea here is that we take the cluster of the entirety of the data and we say, well, how many clusters do we want? Well, we have 10 classes, so might as well say k equals 10. And we hope that every cluster centroid is going to be distinct from each other for each of the k classes, which actually isn't necessarily the case. And when it's not, you have to run into pigeonhole principles issues. So yeah, so we take for every p-test, we take the distance, Euclidean norm, so the Euclidean distance, and we take the minimum distance with the respective k, and that's your classification. One quick note is that this image can be really anything. It can be, because of the 2 norm is fairly robust, the image could be a vector, it could be a matrix, it can even be a function in 2 dimensions, fx, xy equals z. And that's what k-means. For KNN, it's similar, except instead of using centroids, we're just training against the entire train set. You could use best representatives if you want to cut down the size. And we use the Euclidean 2 norm. One thing about this is it's exceptionally slow because in order to get the minimum distance, you need to sort, let's say 10,000 times of size 60,000. That's a lot of sorts. Instead, you could use a bottom, I'm going to say n, usually it's bottom k, but I already used k, bottom n, and we use something called majority vote, and that is basically all the distances go, I'm a 0, I'm a 1, I'm a 2, I'm a 1. In that case, the 1s win, so that's your classification. This actually isn't exclusive. K and N, you can really just implement it within any of these other ones that has a list of residuals or distances. Yet next I use the SVD, which is based off of the linear algebraic singular value decomposition. It's fairly fast, and it can be even faster if you choose to do a truncated SVD. And it's fairly accurate, I say. But this is less intuitive of what's going on here. So like, what is this? What is the structure here? What this is essentially doing is you're taking this unknown digit P and you're doing of the projection of this image P into the subspace that's orthogonal to the span of UK. If you know linear algebra, then that makes sense. And it might even still be word salad. But what that essentially means is that this P is being projected into sort of a subspace, and you want each of these UK or for the classes to be distinct. So when you take the difference between that image and this projection, you want them to be similar or very low residual if it's the correct class, and otherwise you want it to be very high. So you want these subspaces to be distinct. The tangent distance is fairly complicated and fairly technical. The essential idea is that with all of these other ones, we're taking really element-wise tensor distances for every location, and the tangent distance works around that by taking the distance between 2 curves as approximated by the tangent line that's produced as a result of those curves. And it's invariant under small transformations. What that means is you can take a small transformation, like you can rotate the image, you could scale the image, you could shift the image, and it's still going to have the same distance approximately, and therefore it's going to have the same classification. So you can do small changes to the image and still get the right classification. So then moved on to neural networks. This is a very simple schema. The master's students presented a much more complicated schema. Essential idea is we're going to input our X data, which in my case I just flattened, and you have your X data. They have associated weights. I use Xavier initialization. Well, you add a bias and you pass it through an activation function. It has lots of merits like nonlinearity. You choose your threshold, whether it's a phi or not. You can make it within a better range instead of negative infinity. Infinity, it's -1 to 1, maybe something like that. And then that's it within a particular neuron. So we put it within a network, and now you have a neural network. Congrats. I'm not discussing recurrent neural networks. I'm just discussing simple sequential feed forward sort of types. And if you pass information along, these calculations along, you're going to feed forward. But feeding forward isn't enough for it to actually perform the classification. It needs to learn. In order for it to learn, it needs to know how it can do better or how it's doing worse. And we formalize that with a loss, and we calculate that loss with partial derivatives using backpropagation and gradient descent, which is an iterative scheme. The essential idea is we feed information forward and then we trade it backwards. We feed it forward, train it backwards. And we use partial derivatives to tell whether we should go up on the weight, down on the bias, so forth. Next, I moved on to convolutional neural networks for this classification task. My image is 28 by 28 by 1 because I have grayscale image. This is very easily generalizable to by 3 if you have RGB, and then it's just the same structure. We use things like feature detection and feature decomposition. You reduce the size through things like max pool and such, pooling, I should say generally. So we have sort of feature detection, all that with convolution, max pool, and then we pass it through a softmax. And I use cross entropy loss as my loss system. That tends to work better for classification tasks, and we create a probability distribution. I have 10 here because I have 10 different digits classes I could be using. I have times 8 here because that's arbitrary. I could choose to do 4 filters instead for these sorts of things. I wanted to show off my CNN confusion matrix because I felt it was fairly good. And this is out of 10,000, and the marginal accuracies are roughly 99%. There's a couple that's a little under, you can see. So I thought it was all right. So I got a bunch of good results. Well, I shouldn't say that. I got a bunch of results, and I thought, well, how can we do better? We can improve the data, we can improve the model, or we could do meta modeling, and that's what I worked on next. So can we combine these predictions of these probability distributions from each model to get a better accuracy? So I use ensembling to do this. I use 3 different types: uniform average, weighted average, and stacked ensemble. Uniform average it's not a known term. I just made it up. What this means is basically each of these W's, well, actually I should start here. If we have W1, M1, this is a single model. Well, if you just add another model with another weight, then that's an ensemble of models, right? And this is a linear combination. We get an output. And a uniform average is just to say that these W follow uniform distributions, say that they're equal. But the thing about having the same weights is the same as having no weights at all. So it's just M1, M2, M3, so forth, up to N. A weighted average, I try to optimize it. I said, well, this is a linear combination. This is an optimization question. What if we optimize for given M and an output Y, let's say, can we optimize our W and find the global or local optimization? And the stacked ensemble, you put these all together and you put a meta learner over this. I use a logistic regression meta learner. So basically this is its own ensemble, and I put another stack on top of that. Yeah, so I wanted to visualize my my weighted average optimization thing. I couldn't get a global optimization, and then I could only get a local optimization under conditions where I give it a priori information. And I thought, man, that's really weird. There's something's going on here, right? So I wanted to visualize it. So this is an ensemble of only 2 models. The M1 model with weight of respective weight W1 is a really good model, and the W2 is a fairly bad model. What you can see is that very, very quickly as you go along M1, the loss drops down. That's because I define the loss as 1 minus the accuracy, which is really directly the error, really. So there's some drawbacks and advantages of this sort of thing. But you can see in the M1 direction, it's sort of like the loss drops, which means that the accuracy is improving. But as you increase your model, your bad model, you're gonna get more loss, so your accuracy is gonna decrease. There's a threshold point where this model is just so much better, it's just gonna overtake it. And one thing is that the Y scale is 0.4 to 0.05. What this means is you're going from 60% accuracy to 95% accuracy. So this is fairly large. The ensemble, so I looked at 2 different similar models. So now these are similar models, and it seems very bumpy, but now the Y scale is only 0.04 to 0.03, which isn't a lot of an increase theoretically speaking, but it is a little bit of an increase, right? This is because it's sort of, because they're the same model, they're not the same exact model, but the instantiation is the same sort of model. And because of that, it sort of degenerates into this flat area that you see here. This is a discretization of a bunch of weights, and then I construct a manifold from that, approximate manifold of that discretization, which degenerates mostly flat. So here are my results. 3 things to note. Some of these are very fast, some of these are slow. SVD is very fast. Tangent distance and KNN were fairly slow. CNN was very fast. The accuracies, so CNN was much better than its predecessors, and it was pretty good for handling this sort of task. NN, I had 96.9. This can be above or below because there's some stochastic randomness with the initialization. And using an ensemble improved it in every case, regardless of the ensemble. So the stacked did the best, the weighted didn't get much better, but even with the uniform, we still improve our results. So I like to thank everyone. I'm really glad to have attended here as an undergraduate. I'd also like to thank Professor Chen. I started this this sort of project under his data science class, so I'd like to thank him as well. Also, I'd like to share a lot of these things have already been done, so I'm not really doing something super interesting, although the ensemble is a little unique. So my big thing was I wanted to create a sort of a documentation that would allow you to sort of learn these things. So it's sort of like an introduction sort of thing. And yeah, so I go in much more into details on the derivations and all these sorts of things. If you have it downloaded, you can skip around to what you would prefer. So you can look at the derivations of these all this sort of stuff and all that. So with that, I'm happy to take any questions. And thank you for listening.
Marco, that is a really nice GitHub page. Do you mind posting it in the chat? Because it's easier to just click in the chat and it'll go there.
Of course, I'll post it after any questions, if I may.
So for the ensembles, what
Sure.
kind of neural networks are you exploring?
Yeah, so my goal was to use a ensemble for the CNN to hopefully improve this. But I just started with the neural networks because when you have really good accuracy, it's hard to get any more accuracy. So I thought it was most demonstrative of the improvement in accuracy when you use it on something that's good but not perfect. So I used it only on the neural networks. But I hope if I were really trying to get really awesome results, I would use it on the CNN.
Okay. Besides CNN, you haven't really looked for any other neural network.
I looked at neural networks and I used that. So I used a basic neural network. In that case, you're sort of flat. It's best to sort of flatten the data and then feed it as a row or a vector. For CNN, I found that's much better for these sorts of tasks because you can directly input the data of the correct size. I use 2 different infrastructures. So that simple one that we saw before with a single convolution, a single whatever, that's the CNN one, and that's as good as a 96 accuracy. And then what I did is I made it deeper by adding a bunch of extra stuff like dropout, and I go larger, more epochs, that sort of thing. And so to answer your question, yes, I only did CNN, but I did make a deeper network.
Thank you. Seija has a question. Please go ahead.
No, I don't have a question. I just want to send the sum up, okay? Just praising. So it's not a question. I'm really sorry.
Thank you.
Thank you. Any other words of praise or questions from Marco, please? We're so far behind now that it doesn't really matter, but any questions, please?
I had a quick question.
Oh, awesome.
Also, just a general just announcement, advertisement. Most, if not all of the undergraduate, at least capstone projects are on GitHub. And students, if you're wanting to share your results with other people in the Zoom meeting, feel free to just put your GitHub page into the chat window so people can look at it, especially people who have like websites and so on, can run the server by downloading the code. So actually, my question was about the SVD algorithm.
Yeah.
I know there's a free, actually I had 2 questions, but one was just kind of like, can you elaborate on the pigeonhole idea?
K-means? Yep.
Yeah.
So
practice. And then also the SVD, how did you choose K?
Sure. So I'll start with the first question, if I may. You can do more K. So I choose K equals 10 for the K means because I have 10 classes, and theoretically speaking, you would want, if it's unsupervised, you would want it to produce 10 distinct classes, right? It would set 10 clusters, and you'd hope them to be distinct. But if you have 10 clusters, right, 0 through 9, for digits 0 through 9, and any of them repeat, So the cluster is maybe 2 of the clusters become a 9. Well, whichever one is missing is gone. So you're going to get really bad accuracy for that result. So that's sort of what I mean by the pigeonhole principle, where there's only 10 slots. If you produce the same cluster twice, you lose another one. So you get 0% marginal accuracy for that. And for the SVD, I choose k equals 10 because the idea is you take each of the classes and you perform their independent SVDs. So you take all the zeros, you put them together, you get U0, and that's your SVD. You put all the ones together, take the SVD that, you get U1, and so forth up to UK. Now for mine, I only have 10, but if you had a different sort of, data set, you could do however many is respective to your data set.
Great, thank you.
Any further questions, please?
I have a quick question.
Sure.
So first, I like your LaTeX template. It's very nice. This is so far the nicest template I've seen.
Hold on. I'm actually trying to, thank you, by the way. I'm actually trying to find, so I have k-means. Let's go to the results. I'm going to click that. So to, thank you, by the way. To better demonstrate what I was trying to say, you can actually see here that there's no 4 or no 5 in the class. So all of these get 100% error. And this is what I mean by pigeonhole principle. So, but if you have do you have a further question?
Yeah, it's just about the distance. So I think you show a few distance in the last page. I mean, if we can go back.
Sure.
Yeah, right. There are a few principles we can follow. And for SVD, I'm just curious about this one. So usually distance for different objects. So you can see we have p-test and the p-train, things like that. For the third one, SVD, the residual part, it seems the distance is for the same p. So I'm wondering, I just want to know how we can compute the distance here.
Oh, I understand. So what we have here is we have p-test, right? And we're comparing that to p-train, right? That's the two things we're comparing, right?
Yeah.
In this case, we're comparing the image p to this projection of p onto this subspace. This UK is derived from the training set. So this projection of the image p onto here is like our p-train. This object right here performs similarly to our p-train, if that makes sense.
Okay. So after that, what is the meaning? So if the residue is smaller or larger, so what is the physical meaning here?
Right. So basically we have an image P. This is p-test, right?
Mm-hmm.
And then we project that into this space that's generated from our training set. So we take this difference, right? We want the UK such that this subspace, when it projects onto it, it's similar to P. So that would mean that it is a correct projection. What I'm trying to say is if you have P and this isn't actually a 0, right? And you try that against U0, you would hope that projection is mostly the same. So when you take the difference, it's going to be very small residual. But if you tried that same image p-test, which was supposed to be a 0 against U1, that projection is going to be completely different. So when you take that, the difference between this projection and this original image, that's going to produce a very large residual. And this residual is really acting as a distance. If you think about it, I mean, it's mostly the same. And so large residuals mean that the projection was not good, which means that's not a good classifier. Small residuals mean that the projection was good and that it is a good classifier.
Okay, I see. Thank you.
Thank you.
Any further questions for Marco, please? Okay, if not, in the interest of time, let's proceed to our final talk for today. Nicholas Sen.